That's what I said.
Yes.
Yes. Just hold it down. My brother last year bought a bingo.
Thank you.
Like the one that you stand up.
Oh, yeah, yeah.
He bought a new skin, and then he had it for all of 2 months before he sold it.
Really?
Yeah, he was like, this is such a great investment. We know how to rent it, and we just have one. Next thing we just get it out. I was like, okay, but now you gotta go extra length.
Yeah.
How would I be able to make up today's now? I have to take off at like 11:30.
Could you come on tomorrow on Friday?
I mean, on this weekend.
Oh, sorry. I'd have to check the syllabus because I think it's Thanksgiving week. We don't have lab on like that whole
Okay.
week. So then if you could make it up on the Tuesday, we could do makeup lab then too.
That should be fine. Just
Yeah.
not this week.
Yeah, or any other time that we could squeeze it in, like, you know, even if you have to do another double lab another time, like next Friday or something.
Yeah.
All
No,
right.
that should be fine.
Yeah, just whenever we can fit it in.
I got it.
Are you doing civil on school?
I am.
You are. You're doing structure. There's both of them go like this.
I'm the other one, what is it? Practice? He's like, I need a coffee truck. Actually, I think about practice and I haven't done that for tree service. I got pulled over and I'm actively pulled over right now and I don't have insurance. So I did, and I looked at the rates. Like, this is business, like, why are you trying to do this?
Yeah.
I got it. I just haven't graded it, so
Oh, no,
I
it's fine.
apologize.
I just wanted to make sure that you had it.
Yeah, I did get it, so,
Okay.
yeah.
Yeah,
I've
and I
seen it.
finished the student, is there any homework for chapter 6? Or is it just chapter 7? So I was Oh, so 74.
Maybe I forgot to put 6 up there. Okay, I'll try to find 6. Uh-oh.
Okay.
I just have too many papers for one.
Lab term, but not the abstract. This is the lab and emailing the abstract?
Yeah.
Thank you. I'm struggling so much with the abstracts. I'm a perfectionist. I want to read like it would read off of an actual paper, and it's obviously not going to.
He wanted to do that. But then look into that. So actually, I see. Wow, this probably the book was and he bought it. He's like, what? I was like, we shouldn't. He took me to a storage unit and after, it's a movie. He opened it and she got to open it. I feel like you should not do that. Yeah. Like, you're on my mom's right.
They're going to gut it in their reach? That's such a bad, that's the smell so bad.
We started a riot. They were like drinking the beer. The white people. We started a riot. We just started yelling at the people. And we were like, are you guys okay? No. And then we started banging our heads in the door and we just stopped everyone. So everyone went to the cyclones. We're here like dealing with that against it. Just walking. Got to that military place. This man. Dude, I love it. I'm not yeah, I'll definitely get you. Started like this. With the one of my buddies was on. The dude was like in character, but then he stopped. The one that was grabbed his head and kept him.
No. Okay. What's going on? All right, so we'll look at this handout later as we get into covalent bonding. And so let's just start off with our covalent bonds now. So again, right, we had talked about ionic, so that we said that was transfer of electrons. And so now we're at covalent. So again, the big picture is now they're sharing electrons. And so now we can go over some terms formally, and let's look at water. And so again, right, think about the Lewis dot structure, because it starts giving us information. So we're looking at this Lewis dot structure. 2 lone electrons, so again, right, probably wants to make 2 bonds or so. And then again, thinking about that Lewis dot structure of hydrogen, so it has 1 electron, so it's primed to make 1 bond. At least, again, in a typical covalent structure. And so like we saw yesterday with our quick demo, we're going to do that again. So again, we're making our normal bond. And so I drew it a little bit different today, so I'm just drawing it like this at first, right, showing where all our electrons are. So of course this electron came from hydrogen. And then, right, it's also corresponding to our valence electrons. So obviously hydrogen has 1 valence electron, it's in group 1. Same thing with oxygen, right, 6 valence electrons. So this is how many electrons, right, they're bringing to the party, basically, right, for our compound. And so now they form our structure. And so now I'm just going to redraw it, and I'll add our little lone pair symbol here. And so now we have what's formally called our bonding pairs of electrons. So notice, right, I redrew these 2 electrons as a single line. Again, we're showing, right, this is a bond. And usually, again, they're sharing electrons equally. So I would call this a normal bond. Oh, Sorry, this charger is very wonky. All right, and then we have what's called our lone pairs, so our 2 electrons over here. And so notice, right now they're not involved in bonding. But that being said, oxygen can do kind of funky things, and so you might see that later. So for instance, I'll give you a peek at its reactivity. So kind of looking at what oxygen can do. So again, right, we have these 2 electrons. And so something to note now and to carry with you to OChem. So action always starts at your electrons. And so something that our hydroxide, our water can do, is so now these 2 lone pairs of electrons can also kind of grab something. And so this is also pointing at, reactivity, and this would also point at a different style of bonding, right? So this is pointing to a dative style of bonding. All right, so back to just our normal bonds for a second. Let me scooch this on down, sorry. All right, so while I scooch this down, we want to look at the diatomics. And so just start with hydrogen. See if you can draw that, right? Maybe start with the individual hydrogen if you need to. Draw out our structure. So start with H2. What is that going to look like? And then once you finish up with H2, you can probably try fluorine, and then we'll compare those. So kind of check your structures, right? So now just kind of walk through the thought process. So, right, of course, we can start with our Lewis dot structure for hydrogen. And again, right, you can know, okay, they just want one bond. We can see how these two electrons can come together. So now we have just our single bond, right? So hydrogen sharing two electrons. And then what we want to do is we want to be able to analyze our structures that we're drawing, because there's actually a lot of information kind of packed into here. And so we can start with, well, okay, right, each hydrogen, we want to make sure they're satisfied by the duet rule in this case. And yes, right, this hydrogen feels two electrons, and then this hydrogen as well feels two electrons. Okay, satisfied by the duet rule. That looks good. And then fluorine, and of course, right, we could add to this the other halogens, right, chlorine, bromine, iodine. They'd all be similar since they all have 7 valence electrons. So, right, you want to start with your Lewis dot structure of fluorine or any of our other halogens. So again, 7. We see how our halogens, right, are primed to generally make one bond, at least, right, normally speaking. They can do funny stuff, but just starting simply, right, they want that last electron filled. Octet rule satisfied. So again, that's what happens. And so we can also count the total number of electrons to make sure that we didn't mess up. Again, it's pretty trivial right now, but just good techniques. So, right, each fluorine had 7 valence electrons. Yeah, someone want to shut the things. So 7 valence electrons. So that means, so 2 fluorines. So 7 times 2, so we should have 14 electrons in this system. So just double count that, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And again, if you kind of see how they come together, that should be easy enough to keep track of. So you always want to make sure you have the correct number of electrons. And then again, right, octet rule. So this one has 1, 2, 3, 4, 5, 6, 7, 8. So satisfied by the octet rule there. And then of course this fluorine as well, since it's symmetric, right, 8 from there as well. All right, so that's simple enough. So let's continue with the rest of the diatomics and how we might predict their bond. And so let's look at oxygen. So go ahead and see if you can draw a structure for O2. So what do we get in our structure? Single bond, double bond, triple bond? Double. And so before we even draw this structure, right, we can maybe start to predict that just by looking at the Lewis dot structure, right? Because again, we said, well, it probably wants to make 2 bonds. So then, okay, we can take 2 of them. And well, okay, they probably want to make 2 bonds. So, right, we can probably make 2 bonds that look something, you know, like this. And again, keeping track of our total number of electrons in our system. So again, oxygen brings 6 valence electrons times 2. So now we have 12 in the system. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So great, that matches. And then double check that octet rule is satisfied. Right, so 1, 2, 3, 4, 5, 6, 7, 8 for that one. And then 1, 2, 3, 4, 5, 6, 7, 8 for that oxygen as well. And so something else to keep in mind is, so when you're drawing, right, your covalent structures, you know, especially when you're new to this, I want to emphasize that, right, it's all about the process and sketching it. So, you know, let's say you didn't see that right away, that you needed 2 bonds. Well, then just start, okay, you know, you can just start by doing that. Oxygen, drawing a line there, okay, I connected them. And then just start to fill in your electrons, right? So we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? And now we do our analysis. Okay, this one satisfied by the octet rule, but now we notice, well, this one only has 6. And so when you see something like this in a covalent structure, you can start to think, maybe I can move this pair of electrons. And so this is the other thing that you want to start keeping in mind right now, is you don't generally want to move around radicals. Yes, radicals happen. Yes, there are compounds that exist with an odd number of electrons. But for the most part, electrons always move together in pairs. So you want to move the pairs of electrons together. So in this case, we can take one of our pairs from this one and just go ahead and try it in a double bond structure now. And then, okay, now we get our same structure as we arrived to before. So we're kind of seeing that, right? So you want to be able to look at a structure, it's a starting point, analyze it, right? And then how do I fix it to make it kind of make sense? And we'll get into resonance structures as well, because those tell us detailed and powerful information as well. Oh, question? Sorry. And so then something else to think about, though, is, yes, there's still a limitation to the structure. And so I didn't do it this quarter because second quarter we're going to get into the MO diagram and really answer this question. But I'll at least tell you for now that oxygen is paramagnetic, right, which means that it has unpaired electrons. However, right, this is obviously a limitation of our Lewis dot structure. So looking at this, right, everything looks paired and happy, right? We wouldn't expect there to be an unpaired electron. So this is where we have to combine these Lewis dot structures with MO theory. But again, we're going to save this thought. We're going to answer this, and I'll do the fun demo for you guys second quarter. So just kind of keep that in mind, right? A lot of this is we're trying to put all our pieces together to truly understand the nature of these molecules, right? And that's what you're going to kind of understand, is like we're just kind of learning. We're trying to put every piece of information that we're learning to try to figure out how these molecules react, behave, and understand more about them. And then again, chemists are always pushing the limits of bonding, which we'll kind of talk about. All right, so draw out nitrogen then for me into diatomic. So what does that structure look like? What kind of a bond? So what do we get for nitrogen? How many bonds are there? Triple bond, right? So we can look at our Lewis dot structure. Again, we're getting a little bit of information. Okay, it's probably going to generally want to form 3 bonds. We can also see we have less electrons to play with, right? So now each nitrogen has 5, so times 2. So now we only have 10 electrons in the party. And so yes, we should end it with a triple bond. And again, if we were to analyze this, this would also mean that the nitrogen bond is probably shorter, right? Since now it's a triple bond, so 3 pairs of electrons being shared, 6 electrons total. All right, so now let's get into, well, how do we also predict the type of bond? So not just talking about single, double, or triple, but how do we know, again, kind of ionic versus covalent? And this also goes into, length of things, and again, where chemists like to push the limits. And so generally, this is calculated by this difference of electronegativity values. And so like we had mentioned, again, these are calculations that are made with how much a certain atom can pull, right, when it's in a compound. And so that means that fluorine is the most electronegative. And so we can see electronegativity kind of follows that general increasing trend, so up and to the right. And then oxygen and nitrogen are also extremely electronegative. Yeah. So it depends on the difference in electronegativity. And so fluorine is the most electronegative, right? But then to answer whether it's, and again, this is just a kind of in general statement, right? So like I mentioned, chemists are always trying to make new weird bonds. They're always trying to do different things. So this is just considered a general guideline. And so if you have what's considered an ionic bond, that would mean that you have a large difference in electronegativity, such as sodium chloride or like sodium fluoride, right? And so let's just do sodium chloride. I can pull up my calculator. And so on an exam, right, I would have to provide you with some values. So, and we can plug in. So chlorine is 3.16 minus sodium, so 0.93. And so that gives us a difference of 2.23, which again falls into this general larger than 2. And so then we get into polar covalent. So then that's generally considered an electronegativity difference of 0.4 to 2, again, just roughly speaking. And so we can, again, see this kind of continuum as we look here. So again, ionic bond, right, you have complete charge separation, and then polar is just uneven charge. And so we can look at like HCl. And so we can take that difference in electronegativity, so 3.16 minus 2.1, and so we get 1.06, so right somewhere in that range. And then for covalent, this just means equal sharing, so no difference or very little difference in electronegativity. And so again, that's represented by just an even shaped oval, right, showing that again electron density is now evenly distributed amongst the molecule. And so right, all our diatomics would fit in there. So H2, right, F2. So of course, even if fluorine is so electronegative, obviously 2 fluorines have a difference of 0. And so again, this is just a general guideline. So in research settings, right, you also analyze the bond length and yada, 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 and how it compares to other compounds to kind of, again, kind of categorize and characterize a certain compound. And so like we saw, we can also have different number of these bonding pairs. So we saw, of course, we can have a single covalent bond, where, and again, each line just represents 2 electrons. And of course, hydrogen, again, satisfied by the duet rule. Just like in O2, we saw our double covalent bond. We can also see this with oxygen and carbon and many other situations, so carbon and sulfur. So again, those ones tend to double, triple bond. Nitrogen does funky stuff as well. And so again, we can have a triple covalent bond, such as nitrogen, or again, you can see weird stuff with oxygen, kind of more in like temporary states, but you'll still see that. Or again, carbon and sulfur. Yeah.
We talked about orbits in the past. With these, like with the ionic and covalent bonds, does that change the electron's orbits considerably, or do they still kind of share in the same orbit? Or like the shapes of the orbits?
Yeah, so yeah, we'll get into that, but like, so with an ionic bond, that's just going to be a complete transfer. But then once you take two atoms and put them together, right, you take your two atomic orbitals and then mix them to make your molecular orbitals. So then we'll get all into that more second quarter. Does that answer your question? So yeah, basically, like for an ideal back of the napkin calculation, right, you can take your little Lewis dot structure here that you've kind of sketched out, and then you can add MO theory on top of that, and then start to get actually more and more deeper answers that computational chemistry would have to spell out to you. So, right, you can kind of figure this out, kind of guesstimate it, and then, you know, either do it experimentally or put the computational chemistry to work at that point to really prove it. All right, so now let's try some structures, try to practice drawing them. So yeah, let's just try OF2 to start. Does someone want to put OF2 on that board for us? Draw it out. Yeah. Yeah, that looks great to me. So, right, it kind of looks like water, doesn't it? And hopefully it maybe reminded you of water, except instead of hydrogens, right, we have fluorines. Still just make a single bond, again, just like water, and of course fluorine, right? Each one of them we can say has 3 pairs of our non-bonding electrons. And of course oxygen also has 2 pairs of non-bonding electrons. Yeah, or lone pairs, so right, non-bonding or lone pairs, at least in this structure. And so something else that I wanted to point out, and so this is again just like historical reasons and the order that the course has been taught over time. But I don't know why it was made for us not to cover geometry initially. However, I think it's important that when you start to kind of draw these Lewis dot structures that you do think about the geometry. And so we can start to think about the geometry, at least just a little bit. Like I said, we won't formally cover it till second quarter. That's when it's officially in the syllabus, but it's helpful to kind of look at it now just so we can start practicing and again thinking about it. And so if we look at our little Vesper chart here, if you didn't get one, I have more up front. So I'll pull up.
So with things like water and oxygen, trying to name that one. I'm thinking. But
Sulfur.
is that linear?
Oh,
'Cause
so
I always
let's,
heard the shape was more like that, triangular.
yeah. And so if we look at our sheet together, and so we have to orient ourselves with what it's talking about. And so the first thing that it says on this key here, it has these little electron pairs on the side. And so that's referring to either atoms or lone pairs. And so if we look at this oxygen structure, it has 2 lone pairs and 2 substituents. So let's write that out. And so, right, we're looking at our central atom as well. So our oxygen, right, 2 lone pairs plus 2 atoms. So that puts it in 4 electron pairs. And so we can also kind of put, our models with this. Because again, we want to see everything and start to connect it all. I'll just use hydrogens. And so, right, we have oxygen. Sorry, let me do some camera work for a second.
So is the negativity of the electrons why they make shapes like that?
Yes, so that's
Because
getting
they repel
at
each
it.
other, right?
Yeah, so sorry, I'm not doing good camera work. But right, so this is oxygen, and why it's bent like that is because, right, our models are already showing, well, we have electron pairs, occupying this space. They're just not reflected on this model. But then if we take the Vesper chart, right, it kind of lays it out for us. So again, right, we're at the 4 electron pair. So we can say that it has an electron geometry of tetrahedral, right, because it's in this tetrahedral family. But then look what happens. So again, we have our keys here. So BP is saying bonding pair by this one. And so, of course, we go over to our oxygen. So 2 lone pairs, 2 bonding pairs. So, right, it's stated right here. And so now we can see, okay, it's bent. So again, right, you're kind of thinking about the geometry. Again, we'll take it to the orbitals later and understand, what orbitals are involved. But this is a good visual. And so I'm not going to be super picky initially on how you draw them, but again, you do be thinking about the 3D shape. So yes, you want to think about, okay, it's bent, right? Those lone pairs are occupying space, right? They're repulsing, and so we see that as well. All right, let's.
Something like nitrogen, like N2, let's say. Would
Uh,
that just be 2? Would that one be considered linear?
Yeah, so anything with 2 is just considered linear, because this is more for when you have like a central atom with 2 things. So this would be like CS2 or CO2. But yeah, when you just have 2 things, it's just a line. So let's do another practice for a second. Let's just try silicon tetrachloride. So does someone want to put silicon tetrachloride on the board for us? Scott, you going for it? Sweet. And then did you put, yeah, you did. Yeah, just make sure you put all the lone pairs on chlorine, which I think you did. The marker's just a little light. So yeah, that looks good. And that's fine if you draw it flat like that. My brain, I only see a tetrahedral now. So that's how I'm going to draw it up here. And so I'm drawing this little fat wedge here to show that this chlorine is coming out of the plane of the board. And then this dash line is showing that the other chlorine is going behind the plane of the board. And so again, don't forget all your electrons on chlorine. And so we can go back to this Vesper shape and start to see why I only look at it as a tetrahedral compound. So again, 4 electron pair group, except now they're all bonding pairs. And so again, right, that structure is fine if we're just trying to show bonding and where the electrons are. But again, you do want to think about geometry, since geometry is super important with reactivity, especially, again, if you go on to higher level chemistry and OChem. All right, let's look at, we're going to skip around for a second. And so the last little bit of information that we need to analyze compounds is here. So we haven't looked at things with formal charges yet, but you should always be aware of formal charges. And so, well, what is a formal charge? And so really what it is just kind of a way of electron bookkeeping in a sense. And we can see like where the charge is. And so our formal charge are the total formal charges has to equal the total charge of the compound. So sometimes this could mean 0 if we're looking at a neutral compound, We're going to do one in a second that is charged so that there will be a formal charge for sure. And again, that formal charge should add up then to the total charge of the molecule that we're doing. And so, okay, well, how do we calculate formal charge? And so this is for each individual atom, you would have to calculate the formal charge. And so you can do so by this formula. So our formal charge is equal to our total number of valence electrons. And it says in the free atom, right? So meaning just from the periodic table, like your neutral. And then minus, so this says the total number of lone pair electrons. And so this formula honestly kind of confused me. So this means, to me, right, total number of electrons. So total electrons on it. So like every single individual electrons. And then what it's trying to say here, so minus half the total number of shared electrons, I would just say minus the number of bonds. So these are equivalent statements. I just think the way they say it is more confusing.
So, 3 electrons, for example, in water, would that be the hydrogen?
That would be like the 2 little lone pairs here. So,
Oh, okay.
yeah, so let's just practice it for OF2. So again, it should all be 0, but let's double check that. So we'll do oxygen. Sorry, if I could pick a color that I liked. So oxygen, right, to calculate its formal charge. So, okay, 6, right, because it's 6 valence electrons. And then minus each individual electron, so 1, 2, 3, 4. Again, they've phrased it as total number of lone pair electrons. So again, just count up every single one. And then minus, so right, they phrase it as half the total number of shared electrons. So meaning 4 electrons divided by 2. To me, that's too confusing, so I just say minus the number of bonds. So 1, 2 bonds. And so that gives us 0, which we kind of expected because this was a neutral molecule. Again, you could have a positive and a negative charge next to each other. We'll look at strange situations like that. And again, what that tells us. And then double check it for fluorine. And so they're symmetrical. So let's just do 1. So this fluorine, 7 valence electrons, minus 1, 2, 3, 4, 5, 6 individual electrons, minus 1 bond. And so yes, that gives us 0 again. And so again, right, it's about analyzing the structure. Is the octet rule satisfied? Are my formal charges minimized? Because that's the next thing, is usually we don't want a bunch of formal charges in the molecule. So then we want to minimize them, and then we want to put the negative charge on the most electronegative atom.
Are there examples of pairs that have a charge at the end that will maybe connect to like another hydrogen? Like, because you're saying that there's the complex.
Yeah, so I think, let's see. Let's try ammonium first, and then we'll try to do CO, because CO is funny. So start with ammonium. So draw that out. So NH4.
Can you also scroll back to where you got the
So nitrogen only makes 3 bonds until it doesn't.
Okay.
So I'm going to start going through this in the interest of time. And so I want to point out a few ways to approach this, right? So we can think about just adding up all our total number of electrons. So, right, nitrogen brings 5 electrons, 5 valence electrons. Each hydrogen brings 1. And then remember, with our plus charge, we need to adjust our total number of electrons. So I like to put our plus charge, which of course that means we have to subtract. So now we only have 8 electrons. And so then this kind of falls out nicely. So we can just start connecting, our 4 lines to our hydrogens. And that works, right? 1, 2, 3, 4, 5, 6, 7, 8. I'm done. So that's one way to approach that. And so where does our formal charge go? Because in this case, right now, we actually have a charged molecule, right? Our polyatomic ion. So that means we have to have a formal charge somewhere. So who's carrying the formal charge? Yep, so our nitrogen, and right, we can just verify that. So formal charge for nitrogen. So 5 valence electrons minus 1, 2, 3, 4. So 1 plus. And then on your structure, you want to draw a little plus charge there with a circle to show that that's where it's located. And so I do want to at least kind of show you, well, where did this come from? Right? We had just talked about, well, nitrogen can make 3 bonds typically. But, right, we want to start thinking, again, in other ways that they can be reactive. And so ammonia is one of those ones that can do stuff, or nitrogen, again, can do a lot of stuff. And so this is going into acid-base chemistry now. But again, you just want to start to appreciate what can happen. So, okay, right, those 3 electrons are these are already tied up, right, in bonding, so they're all bonding with each other. But we do have this lone pair. And so, yes, it can initiate some action. And so this is already explaining why ammonia is a base. So again, action starts from the electrons, and it would pluck off that hydrogen, and that gives us our ammonium and corresponding hydroxide. So that's just, again, to give you the piece of the chemistry, right? And then this starts to go into, well, that's why chemists like playing with nitrogen, and it makes really good main group chemistry because, okay, it makes 3 bonds, but then it can start to do funky stuff with that lone pair, right? So that's something to start to recognize, that that lone pair can do extra.
Did the nitrogen make that fourth bond if it only has?
Because of the 2 lone pairs, right? So yes, it had 3 electrons, right, initially just naked, but then, okay, those were occupied in bonding. But that being said, now this
So I have
oxygen.
an extra negative charge that is in the hydrogen?
Yeah, so right, this
Okay.
negative charge. And so this starts to get into, well, hydrogen kind of has this partial positive on there since oxygen is electronegative. So now we're starting to get into polarity. But yeah, so that's all starting to build onto reactivity. So that's just a preview of where we're going with these structures, and again, showing you the power of these structures. And so one more quick example, since you brought up a good question of, well, what is this showing us? And so try the structure of CO and analyze it, do your formal charge analysis, and let's just see what we come up with. So does someone have a structure for CO that they want to put on the board? Right, it's fine if you don't know if it's correct or not, right? We just need kind of a starting point to analyze.
I have an idea.
Yeah, let's see what you've got so far, and then we can talk about it.
See, but then I don't know what happens with these others. So maybe there's a little bit of a negative here of these two.
So how many lone pairs do you have in carbon? Sorry, I just can't quite see the marker.
So I have a carbon double bonded to an oxygen, which would satisfy the octet for the oxygen, because I'm not sure about the carbon. Because it makes 4 bonds, right?
Well, up to, but, okay, so we have,
But it doesn't have to? That makes more sense. Okay.
yeah. So then we have 10 total electrons, right? So 1, 2, 3, 4, 5, 6, 7, 8. But then I have 9, 10. So I feel like we only have 2 left over. And so we could play with this, though. So, okay, we're here. Right? So again, this is most important, is just start with the correct number of electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, just double counting. So what could we do then? What do other people do? So, okay, what if we triple bond it? So you want to take this lone pair from oxygen and put it in. So let's analyze that structure. So now it looks like we're looking at something like that. And, okay, octet rule appears to be satisfied. So 1, 2, 3, 4, 5, 6, 7, 8. Same thing for oxygen. But now what happens when you do your formal charges? So it has 4 valence electrons. So that just means like that it brought 4 to the party,
Yeah.
right?
That doesn't mean that's not necessarily completely bound to how many pairs it can, or how many bonds it can make.
Yeah,
That's just how
'cause-
many electrons it can make.
Right, yeah. So it's just, you first just take the total number of electrons, right? And then you're trying to see, well, where are they going? And I think you're catching on to kind of the troubling part about the structure, but then we're going to find out that the troubling part actually tells us something. Because I think you're recognizing, so do the formal charge of carbon, and that'll answer, I think, what you're troubled about. So it can make up to 4, but yeah. That doesn't mean that it always makes 4, so. So what's the formal charge on carbon? So -1, right? So let's go through that. So carbon, right, 4 valence electrons, like y'all mentioned, -2 lone electrons, -3, so -1. So yes, you are correct to be suspicious, right? It's carrying probably more electrons potentially than it should. And this also kind of violates that rule that I had mentioned, right? Because I said, well, normally you want to put the negative charge on the most electronegative atom. And so for oxygen, if we compare, so 6 valence electrons, -2, -3. So obviously that has the 1+ charge. And so this is troubling in some sense, right? We could try to play with it, we could try to move it around, but we really won't find a better structure. But what's interesting to note is this actually reflects then the reactivity of CO. So CO then actually is known to bind to metals by the carbon. And so again, now these 2 electrons are going to go on and attach themselves to a metal.
And this is how polyatomics work, right? Like your
So this would be more like metal ligand interaction. So this, since CO itself, it's not a polyatomic ion, right? So it's not charged because it's overall still neutral. But yeah, but then it can act as what's called a ligand, which just means that it can bind to a metal. And so I'm drawing it in such a way as well to emphasize, in this case, that CO is donating to nickel. So, right, so again, this is showing reactivity. So we have this really electronegative carbon, right? And we can also verify this by computational chemistry. So again, even though it seems strange that the negative charge is on carbon, computational chemistry would verify that yes, there's a large electron density on this carbon, and then reactivity reflects it. So yes, when CO binds to a metal, it binds by the carbon, by that lone pair, not by the oxygen lone pair.
With the carbon, can you go over really quick that equation? So it's 4, 2, and 3.
Yeah.
4 is the total amount of bonds it can make.
4 is the valence electrons,
4 is valence electrons. Okay, 2
is the individual.
the lone pairs.
Yeah, so like each lone pair. So right, it
So
says
it's
count.
2 pairs of lone pairs.
No, one pair lone pair, but
Well,
you
one
count
pair.
them individually.
Makes
Yeah.
sense. But where did the 3 come from?
And then the 3 is the bonds, number of bonds.
I
So
thought you said carbon made 4 bonds.
4 bonds total normally, but then you
It
look at how
depends
many
on
are in the
what.
structure.
Okay.
Yeah.
Oh, okay.
So then number of electrons. Yeah. So that's where, again, like normally if you're just kind of playing around with it, you'd want to get the negative charge on oxygen because it's the most electronegative. And so that's, again, where you kind of like look at all your potential structures and figure out like, you know, which is better based off of where the formal charge is. So it is kind of like a little bit of a guessing game, kind of playing around with it. But then we're just bringing up CO since it does just violate that rule. And
So in your structure there for the nickel, the electron configuration for nickel is 4s2 3d8. So with that formation, it fills up the 3D shell, and then it goes on to fill up the P-block shell, like to make that
yeah.
solid valence shell.
Yeah, so then this would be satisfied, you know, not to go down into too much transition metal chemistry, but yeah, that would be the 18 electron rule would come into play here. Exactly, but, you know, that's, again, kind of going, that's showing you where we're going, and again, the power of these structures and how you can see all that
How would
reactivity.
you write that as chemical? Like, how would you write that? I have Ni, I have the nickel in parentheses CO to the subscript of 3.
I mean, I don't know if this is actually how you make it, but yeah, just like nickel tetracarbonyl, is that what you mean?
Yeah, that's
Yeah. But I'm not actually sure if that's the correct synthesis, and then, yeah.
I guess to follow up, the CO is linear,
Yeah,
and then the nickel is tetrahedral
yep,
with those linear bonds.
yeah. Yeah, and what's strange is like, so your compound chemistry thing, it makes this comment that it fails for transition metals, but I don't think that's really the case, so I don't know why they put that statement in there. But anyways. Oh, and another fun fact, so nickel tetracarbonyl is, you would not want to work with this. This is actually a liquid substance that is so dense that it would fall out of your fume hood, so the fume hood does not provide enough flow rate to work with it. And then it's dangerous because if you inhale it, then the CO obviously like releases and the nickel binds to you, so then you get nickel metal poisoning. So yeah, fun stuff. Anyways, all right, now I've rambled way too much, so we will end there. I'll go ahead and pass out the quiz. Again, if you need to take a break, go ahead and do so. And then I will also pass back your exams. Oh, and then I will pass back, so I've been slowly making my way through your grading. I need to catch up on entering. But I do have a few observation labs or other labs with no names on them. So if you could look at them. So I can sort out what's missing. All right, let me get the quizzes out. Again, take your break if you need to. Try silver here, or entering, or something.
Yeah, I should probably do something.
Huh? Oh, sorry.
Probably check what I'm missing.